So we talked about how by knowing the degree of a polynomial function, right, and remember that polynomial functions are in the form of axn plus bxn minus 1 plus cxn minus 2 plus, and let's just keep going, let's say to e. N is the degree of the polynomial, right, and the degree is the highest power of the polynomial function, right, and a is the leading coefficient, and ax to power n is your leading term. Now we said that by knowing the degree of the polynomial function, we can understand the behavior of the function as well as the end behavior. We said that even degree polynomial functions have similar end behaviors and odd degree polynomial functions have opposite end behaviors. We also looked at, variations of a positive and negative even odd degree polynomial function and how those end behaviors were different, which quadrants they would end up in, right? Now, using the degree, we can also figure out how many extrema or maximum minimum points that can exist in a function, right? And this is what we call a turning point. A turning point or a turn are basically points of extrema, and they include maximum, minimum points. They also include points of inflection. Okay, so a turning point can be a point of inflection as well as a point of extrema. Now, what are points of inflection? Okay, I use POI for points of inflection and POE for points of extrema. Okay, well, we stated that points of extrema are maximum minimum points, right? So if the curve ends up here and then this is a maximum, right, this is a point of extrema, so this is a max. Right, in another case, if the curve is concave down, this is a point of extrema, and this is a minimum point. Okay? A point of inflection is where you have a change in concavity. So for instance, if the curve here is concave down and it goes concave up, so this is a point of inflection, right? So this portion here is concave down, this portion here is concave up, right? Or in another case, we have a concave up portion, and then the curve basically becomes concave down here. Okay, and this is another point of inflection. Okay, so all of these things are examples of turning points. I'm just going to look at turning points as turns, right? So we're going to call them turns, and it's really useful because we can use the degree to figure out how many turns you would possibly find in a function, right? And the maximum number of turns a function will have, I'm going to use t to represent turns, is 1 less than the degree. Okay, so put another way, n minus 1 should be equal to t, right? So the maximum number of turns that any function will have here is always n minus 1. Okay, so this is really useful, right? Because if we have a degree of 1, right, if we have a cubic function, right, so the degree here is, sorry, a degree of 3, not degree of 1. A degree of 3, we should expect a maximum of 2 turns. Okay, so an example of 2 turns, an example of a cubic function, something that kind of looks like this, right? You can imagine that there is a turn, or there's a maximum here, and then there's a minimum here. Okay, so there's a turn here and a turn here. Okay, so that is an example of a turn, right? So there's 2 turns here, which is consistent with our notion that the turn here is the degree minus 1, so there's 2. Right, so that's really the idea, right? So this is a really useful notion to kind of understand. Furthermore, these turns or points of inflection are going to be usually located in between the x-intercepts. Okay, so for instance, say this is your graph. Okay, let's say that there is a y-intercept located here, right? You can notice here that this type of function, right, if it's opposite end behaviors, right, negative infinity to positive infinity, right? So this tells us, and we know that the end behaviors are extending from quadrants 3 to quadrants 1, right? So this is basically going to be a positive odd degree polynomial function. Another characteristic that we can understand here is there should be two turns, right? So one of the turns I showed, there's a minimum here at the y-intercept, and there should be a maximum here. So there's a maximum here, there's a minimum here. So potentially this is a cubic function, right? Because we can understand that the turns is the degree minus 1, so the degree here is turns plus 1. So because there is two turns, right, the degree should be 3. Okay, so it's really useful to kind of understand this. But specifically, these are two examples of points of extrema. Now let's say we knew the x-intercepts. Okay, now we know what the minimum point here is, but say we knew these two x-intercepts. And let's call these points A and point B. Okay, so the intercepts are A and 0, right? And the other intercept is B and 0, right? And you can imagine that these are negative, right? It's not too important, right? A is a negative number, B is a negative number, right? So A and B are both less than 0, right? Now, the idea here is that there is a maximum point located here, and the maximum point, or this point of extrema, will always be the midpoint, right? The x value of the maximum point is always the midpoint of the x-intercept. So the x value of the turning point, we'll use turning point to represent, because it can be used for minimum points as well. The x value of the turning point is basically the midpoint of the two x-intercepts. So you can think about it as a plus b divided by 2. Okay, and if you wanted to figure out the y value of the turning point, which is the maximum point in this case, right, the y value of the turning point is basically f of a plus b over 2, or you can just plug in f of the x value. You plug in the x value of the turning point into the function to find the y value, just like how you're used to doing it, right? So this is a really useful idea to kind of understand, right? Now, we need to also consider the domain and range of these polynomial functions. Now, we know that this is a positive odd degree polynomial function, but you can understand that the end behaviors here, positive infinity, negative infinity, they'll span the whole range, right? They'll span the whole range of the Cartesian plane, right? So because they'll span the whole range of the Cartesian plane on the y-axis as well as the x-axis, the domain for a positive odd degree or an odd degree polynomial function and you can actually memorize this, but it's good to understand it. The domain and range for all odd degree polynomial functions are going to be constant. X can belong to all real numbers because there is no restriction for the domain, and the range here, y can belong to all real numbers. So because there is no restriction for the range, specifically, right, all of these maximum and minimum points are not absolute. And absolute means that they will restrict the range, right? These maximum and minimum points are what we call local maximum and minimum points. And it's because these maximum and minimum points don't restrict the range of the function, right? So these are all examples of local maximum and minimum points. So odd degree polynomial functions will only contain local maximum and minimum points. Now, in some cases, you will have some questions will mention absolute maximum and minimum points, but that's only within a given interval. Like if you have a given interval, restricted intervals can include absolute max and minimum points, right? So if you have a restricted interval, you can have absolute max and minimum points, but a general domain where x belongs to a set of all real numbers, so a free floating domain is like what I like to call it. In that sense, you would only have local maximum and minimum points. Okay, However, if you're looking at an even degree function, okay, let's just draw that here. Okay, so if you're looking at an even degree function, you can imagine that this is even degree because both of the end behaviors are the same. They're in quadrants 1 and 2. So this is an example of a positive even degree function, right? If you're looking at even degree function, you can note here that this guy here has 3 terms, right? So if it has 3 terms, then the degree of the function here should be 4. Okay, so this is an example of a quartic function. It's a degree of 4, right? And you can also see there that there are 3 different points of extrema. Okay, so I'm specifically just looking at the y-axis, but you do want to include these points of extrema, right? So let's say this is -2, and this is like 4, and this is like 1 and 6. This isn't drawn to scale, guys, so just bear with me here. This is -2 and 4, this is 1 and 6, and then this is like, let's do 3 and -6. Okay? You can imagine here that the domain will encompass all points. Okay, the domain actually will encompass all points because there is no restriction on the x values. It just ranges the entire span of the x-axis. The range, on the other hand, is limited. There is a restriction, and the restriction here, y belongs to all real numbers, but the lowest point that the y value can touch is greater or equal to -6, right? So this point here, the 3 and -6, is what we call the absolute minimum because of the fact that it restricts the range, right? Restricts the range. However, we can also notice another minimum located here at the -2 and 4 mark. -2 and 4 is another minimum, but this one here is called a local minimum. Okay, so you can have multiple minimums and maximum, multiple minima and maxima in a function, right? But there's only going to be one absolute minima or maxima for each scenario, right? So this is the local minima, and because we had an absolute, so the absolute will only restrict the range, and then this here would be the local maxima, right? Or the local maximum at 1 and 6. So 1 and 6 represents the local maximum. Okay, so this is really important to understand, right? That the terms is always 1. The maximum number of terms a function can have is 1 minus the degree, right? And we'll only have local extrema in odd degree functions, and you can have local and absolute extrema in even degree functions. Okay, so with that being said, let's do some questions regarding characteristics of polynomials.